Imagine you're walking the dog down a city sidewalk. Under that concrete, just a few inches below your shoes, there's a living internet of fungi. So long that end to end, it would stretch about 68 quadrillion miles. Yeah, quadrillion with a Q. Now, that number is mind-boggling, so let's zoom in. Picture a single strand of this network. It's called a hyphae, and it's so thin you could lay a few hundred of them across one human hair. Yet, in 1 teaspoon of lively soil, those hair-fine threads could run hundreds of meters if you stretched them out. Wild, right? First signpost: how the network is built. Roots are the doorways. Wherever a plant root bumps into soil, fungi knock and ask, "Got room for a roommate?" If the plant says yes, that root tip becomes another on-ramp to the underground superhighway. In 1 gram of soil, think a paperclip's weight, thousands of these entrances can switch on or off depending on moisture, temperature, or even who the plant's neighbors are. Here's a quick example. In some forests, most of the phosphorus a tree uses has ridden partway inside fungal tissue. Roots alone can't reach the tightest soil pores, but hyphae can. Flip that around and you get carbon flowing the other way. About 4 billion tons of CO2 equivalent carbon enter soils every year through these fungal channels. Let that sink in for a second. Third signpost: how we know all this. A group called SPUN mashed up tens of thousands of soil samples with satellite data on climate, vegetation, and land use. Then they let machine learning models connect the dots. The result? A first-ever global estimate, roughly 110 quadrillion kilometers. Again, that's about 68 quadrillion miles of hyphae, nearly all in the top meter of soil. If you could lay those filaments end to end, they'd lap the solar system dozens of times, all while staying hidden right beneath our feet. Okay, cool science fact, but what does it mean for you and me? Practical takeaway number 1, climate buffering. Think of these fungi as secret detours where carbon can pause instead of sprinting back into the sky. The thicker and healthier the network, the longer that carbon break lasts, and the cooler our planet stays. Practical takeaway number 2, plant resilience. Because the network shuttles water and nutrients, plants tied into rich fungal zones bounce back from stress faster than their unconnected twins just a meter away. Farmers notice higher yields under heat waves, city foresters see street trees survive cramped sidewalk pits, and restoration crews watch seedlings recover after drought, when, and only when, the right fungi are on the job. Practical takeaway number 3, fragility. Plowing, bulldozing, or paving over land can slice these networks faster than they can regrow. Even heavy fertilizer can thin them out. If nutrients are handed out for free, plants stop investing sugars in their fungal partners, and the web begins to fray. That's why conservation groups now list underground biodiversity right next to saving rainforests and wetlands in their climate playbooks. Story break. Walk through a meadow, and the plants look like neighbors sharing a fence. Underground, they're more like tenants splitting utilities. One patch pays with extra sugar to get priority water during a dry spell. Another skimps and lands last in line. Ecologists have watched cloned seedlings, genetically identical, live or die purely based on which side of that invisible vulnerable fence they're on. It's that dramatic. Looking ahead. Restoration folks are starting to act on this knowledge. Instead of just replanting trees, they move small chunks of intact forest floor, called inoculum, into new sites. By seeding those starter fungi, roots can plug straight back into the superhighway. Desert edges, city parks, even croplands each hold a unique underground community. Learning the strengths and weak spots of each could spell the difference between a landscape that looks green now and one that stays green 30 years from now. Big unknowns. First, how fast can these webs rebuild after we bulldoze them? Second, will future fungi adapt to hotter, wilder weather in ways that change where forests can survive? Scientists are racing to find out. So here's what we covered today. 1. Beneath every step you take lies a fungal superhighway about 68 quadrillion miles long. 2. Roots are merely on-ramps. The real traffic, water, nutrients, and carbon, moves inside hair-thin fungal threads. 3. That traffic locks away roughly 4 billion tons of carbon each year and keeps plants resilient during droughts, heat, and pests. 4. Plows, pavement, and over-fertilizing can slice or starve the network, but smart restoration, like adding fungal inoculum, can stitch it back together. 5. Protecting this underground web might be as critical for climate and biodiversity as saving the forests we can actually see. Next time you pass a tree, a park, or even a crack in the sidewalk, remember, you're walking on top of an unseen, planet-sized collaboration. Treat the ground kindly, and that hidden network will keep buffering our climate, feeding our crops, and holding our ecosystems together. That's power you can't see, but now you know it's there. Thanks for listening. On our next episode, we'll dig into how roots choose which fungal allies to invite and how that choice shapes entire landscapes. Stay curious, and I'll see you then.